Have you ever bounced a ball and wonder what made bounce possible? Or sip from a bottle and forget the polymer holding it together? Today, rubber and plastic, two materials that quietly shaped the modern world, are the topic of today's Things You Don't Know episode.
That sounds very interesting, Dr. Weaver, from ancient sap to space age polymers. And now the environmental bill is unfortunately coming due.
So, as I said, welcome to Things You Don't Know.
We're taking a two-lane road today, rubber on one side, plastics on the other, sometimes merging, sometimes colliding, especially when we talk about the planet.
We'll track the tech, the geopolitics, and the impacts from Mesoamerican ball courts to microplastics in the deep sea. Natural rubber begins as latex, a milky sap tapped or from trees. Mesoamerican cultures, including the Olmer, Maya, and Aztec, harvested latex from Castilla elastica and mixed it with juice from the morning glory vine to vulcanize. Centuries before the word existed, they made balls, bindings, and waterproof fabrics.
In Europe, rubber trickled in during the 18th century as initially a curiosity. Erasers, and they're still called this in the UK, were literally rubbers. But it was sticky, brittle in cold, gooey in heat. Enter Charles Goodyear in the 1830s and 40s. He stumbles almost literally into vulcanization, heating rubber with sulfur to create crosslinks. Suddenly you get resilience, elastic, durable, and temperature tolerant.
Vulcanization unlocked hoses, gaskets, belts, and the guts of the Industrial Revolution. Then, in the late 19th and early 20th centuries, the tire arrives and rubber demand explodes.
Geography matters, friends. Wild Hevea trees in the Amazon were spread out, nature's way to slow the pathogens. But seeds smuggled to British colonial botanic gardens led to monoculture plantations in Southeast Asia, Malaysia, Malaya, Ceylon, now Sri Lanka, Borneo. Huge production, but also deforestation and labor controversies.
World War II created a shock. Japan captured most plantation regions. The Allies lost access. Synthetic rubber, styrene butadiene rubber, or SBR, scaled up fast. The U.S. built a massive program almost overnight. Other synthetics like neoprene and nitrile followed for oil-resistant or specialty uses.
Today, rubber is a family. Natural Hava latex and synthetics like SBR, BR, butadiene rubber for tires, EPDM for roofing, silicone for medical tubing, even polysporine that mimics natural rubbers for surgical gloves.
Plastics start as problem solvers for scarce materials. Celluloid in the 1860s was sold as an ivory substitute for billiard balls and combs. It was flammable, kind of spectacularly so, but it proved a point. We could design materials.
Then Bakelite in 1907, first fully synthetic plastic. It was heat resistant, electrically insulating, perfect for early radios, telephones, and appliance knobs. And by the mid 20th century, a polymer Big Bang, PE bags, films, bottles, and low and high density variants. PP, hinges, food tubs, automotive parts, PVC pipe, siding, medical bags, versatile but additive heavy. PS, foam clamshells, insulation, brittle and solid form, PET soda bottles and fiber, think fleece and polyester, nylon parachutes, stockings and gears, PTFE, Teflon, slick cookware coatings and seals.
Plastics democratized goods, cheap, light, and moldable. Single use convenience soared, especially after World War II with suburban supermarkets and disposable culture.
And composites joined the party. Carbon fiber and glass fiber plastics made cars lighter, planes more efficient, wind turbine blades possible, medical breakthroughs, sterile packaging, syringes, heart valves, catheters depend on plastic and synthetic elastometers.
In short, if rubber gave us flex and seal, plastics gave us shape at scale.
Tires, yes, but the list is wild. Vibration isolators in washing machines, engine mounts, O-rings in spacecraft, shoe soles even, athletic turf infill, pencil erasers, weather stripping, condoms, and even surgical gloves.
Plastics hide in plain sight. Circuit board substrates, insulation on every wire, IV bags, solar panel back sheets, refrigerator liners, realistic prosthetics, 3D printed parts, packaging that keeps food fresh and reduces spoilage.
Unfortunately, there's a paradox. Plastics often save energy and prevent waste, lighter vehicles, longer food shelf life, while creating a downstream of waste and a toxicity challenge.
Yeah, that is true. Let's split the cost into four different buckets: resources and emissions, land and biodiversity, waste and leakage, and health and exposure. Now, most synthetic rubber and most plastics are petrochemical products derived from oil and gas. Extraction, refining, and polymerization carry a carbon footprint. Plastics manufacturing is energy intensive, and incineration releases CO2, and if poorly controlled, toxic byproducts.
Natural rubber is biologically based, but it's not impact free. Monoculture plantations can drive deforestation, peatland drainage, and soil depletion. When forests are cleared, stored carbon goes airborne and biodiversity plummets. Southeast Asia's rubber frontier has replaced diverse forests with single species stands. That fragments habitats for orangutans, hornbills, and countless other understoried species. Plantation chemicals also affect soil life and damage waterways.
Alternative crops like anguille in the U.S. Southwest and Russian dandelion are being developed to diversify supply and reduce pressure on tropical forests. Of course, if we listen to our president, none of that really matters because, hey, it's okay. Drill, baby, drill. Pollute, baby, pollute. It's cool. Plastic waste is now a geological signal, even if many people don't choose to read it. Rivers carry it to coasts, winds blow light fragments into remote regions. Microplastics show up from mountain snow to deep sea trenches. Fishing gear, packaging, microbeads legacy, different sources, same result, persistent fragments.
Tires also deserve a spotlight as we drive. Tiny rubber and additive particles abrade off tire wear particles. They are a major source of microplastics in urban runoff, ultimately reaching waterways. Heavier vehicles can worsen abrasion, so EV weight is a factor. Through regenerative braking, reduces brake dust.
Yeah, that's true. Biodegradable isn't a magic word. Many bioplastics, like PLA, require industrial composting conditions, like heat, moisture, microbes, to break down. In the ocean or a cool backyard pile, they can persist. Oxo-degradable additives, just add fragment material, are now widely criticized. Out there in the Pacific floats what many call the island of plastic. It's not on any map. Well, actually, it is on a few, but it's larger than France, and growing. Now, Dr. Deneen, what do you think the story is here?
Well, it's not really an island. There's no palm trees, no sandbars. It's a gyre, a swirling current where discarded plastic collects. Think bottles and bags, fishing nets, and tiny particles, microplastics clumping together. It's a monument, if you can call it that, to human convenience.
And the impact beyond the eerie image of a continent of trash.
Marine life pays first. Turtles mistake the plastic bags for jellyfish. Birds feed bottle caps to their chicks. Fish inhale microplastics, which then cycle back onto our dinner plates. It's not just out there, it's in us, friends. Studies find microplastic in the human bloodstreams now.
Hmm. Yeah, but there's no climate change, no pollution. Don't worry about it. That's what some say. So the legacy of this so-called island isn't geographic, it's generational. Plastic lasts hundreds of years. A bottle tossed in 1970 could still be bobbing in the gyre while the owner's grandchildren are alive.
Exactly, it's the sharpest reminder of how modern waste outlives us. The ocean currents don't lie, they show us what we've left behind.
Maybe forces us to ask, what kind of island do we want to build for those who come after us? One of waste? Or maybe something better?
Plastics and rubbers are mixed with additive, plasticizers, flame retardants, stabilizers, and antioxidants. Some, like BPA and certain phthalates, raise endocrine disruption concerns, prompting reformulations and regulation for food contacts and toys in many regions. Safer chemistry is improving, but transparency and standardization, as with so many other things, still lag.
Inhalation and ingestion of micro and nanoplastics are active research frontiers. We have growing evidence of widespread exposure. Exact health outcomes are still being clarified. Prudence says reduce unnecessary microplastic sources and improve filtration at wastewater and stormwater points. We need to design for circularity, make products from a single polymer where possible, label clearly, avoid dark pigments that confuse optical sorters, design parts to snap apart, standardize caps, threads, and closures.
We also need reuse systems, refill stations, returnable packaging, durable takeout containers with a deposit loop. These cut single use demand. We need to pair that with EPR, extended producer responsibility, so companies fund collection and recycling infrastructures.
Mechanical recycling works best for clean, single resin streams. PET bottles are the poster child for that. Advanced recycling, like various chemical depolymerization or polyresis approaches, aims to turn mixed plastic back into monomers or oils. promising in some cases like PET or PA, but watch energy use, emissions, and quality control.
What we also need is material innovation. High silica compounds for tires, for example, improved tread designs and capturing devices are being prototyped to get rid of the tire dust. A bio-based polysoprene for rubbers, dandelion sourcing, certification schemes like FSC for natural rubber, and multi-stakeholder groups to protect the forests and the labor. Bio-attributed polymers and plastic, enzyme-assisted recycling, think PET, eating enzymes, and an additive reformulation to cut out on toxicity. Wastewater plants need better filtration upgrades to trap microfibers, stormwater treatment for tire particles.
Yeah, single-use bans and fees, deposit return systems for bottles, recycled content mandates, procurement standards for governments, and right to repair laws that lengthen product lifelines.
There's one myth we have to discredit, and that's that all bioplastic disappears anywhere. Many need industrial composting. Without it, they can persist like conventional plastic.
Another myth: natural rubber is automatically sustainable. The reality: it can be, but only with strong land, biodiversity, and labor safeguards.
The saddest myth is that recycling alone will fix plastics. It helps, but source reduction and reuse are really essential.
Well, there we go. Rubber gave us resilience, plastics gave us shape. Now the challenge is responsibility.
We need a smarter design, a cleaner chemistry, better systems, so a bouncing bottle don't bounce back on our planet.
All righty. Hope you've enjoyed this. This has been Things You Don't Know. And come back and join us again. We have some good stuff coming.
Please leave a like and comments, folks, and we're looking forward to seeing you again. So long.